Well, I would like to thank the organizers for inviting me and a chance to give this a virtual talk. This topic really started last year when I visited IPAM, so it's kind of highly motivated. And the idea is to see whether one can use some strategies that has been used successfully in Google AlphaGo Zero in solving certain optimal control or game problems. And personally, I have been kind of interested in this type of problem concerning line of sight. So in this talk, I will interchange the word line of sight to visibility from the visibility from observation location. I will interchange these two concepts. And this is a joint work with one of my current students who's actually graduating in a month, Louis Lee. Okay, so the motivation of looking at algorithm in solving this type of problem is the following. So there are more and more availability of range sensors such as LiDAR sensors where you can get the distance from observer's location to boundaries that obstructs the line of sight of this observer. And usually these boundaries is obstacles that if you think about the observer being a robotic agent, then you cannot penetrate the obstacle, so you need to avoid it. So we're thinking about applications related to autonomous robotic agents, UAV, etc., and they're performing tasks that involve certain, optimizing for certain objectives involving visibility or involving the line of sight from these autonomous agents. So these kind of problem, of course, if you're in a simply connected domain, star shape, then the problem is perhaps not as challenging as when you have a lot of obstacles in the domain. So you have domains with holes and no longer simply connected, and your line of sight are blocked, and so it's a lot more complicated to optimize objectives related to line of sights. So this talk is about our kind of experiments and current ideas on how to solve this kind of problems. To begin with, I will first describe, a few such kind of problems. So the first type of problem, which will be the main focus of today's talk, is we call it surveillance-evasion games. So in the typical game here in 2D, there's a pursuer, and in this talk, the pursuer is always colored. The good guy, we like to pretend, the pursuer is always colored in blue, and then the evader, the adversary agent, is always colored in red. And they are moving around. In this case, if you see the movie on the right side, they're moving around a simple domain like that with an circular obstacle in the middle. The gray region denotes the region of occlusion from the pursuer. And they play a non-cooperative game in the sense that the red guy is going to try to vanish from the visibility from the blue guy. And the blue guy can manipulate, of course, the shape of the gray region in order to try to keep the red guy under his surveillance as long as possible. So we can define a very strict endgame condition as the game would end the moment the red guy will get into the gray region. Then you lose. You can no longer retrieve this guy. Or you can relax this endgame condition into something that will make, in my opinion, make the game a little bit more complicated to solve. For example, you say that you have a total time budget for the red guy to vanish from your eyesight. Say 5 seconds in an hour, this guy is allowed to vanish from your eyesight. No more than that. If you lose more than 5 seconds of the bad guy in your eyesight, then you lose the game. And of course, you can generalize this kind of game to have multiple players, uneven number of pursuers and evaders. So the problem is global, because the line of sight, the reach of line of sight is, we assume that it's global throughout this piece of square domain. And in this talk, we'll focus on how to be a good pursuer, how to be an effective pursuer. And so, by the way, this video simulation, this video clip over here is actually a simulation computed by the algorithm that we will discuss today. So it's played autonomously without human intervention. And you see from here, the blue guy, so let me start again. So the blue guy kind of move in the right place, and at points, at some situations, the blue guy now will stay fit, not moving, until the red guy reaches certain kind of critical region in space, and then the blue guy decide to chase, march in in certain direction that optimizes the prolongation of the games. Okay, so the other type of problem that we have endeavored, which will not be discussed today too much, is this patrol and surveillance game. So you can think about, there are this good guy and the bad guy, and the bad guy is moving and try to hide away as in the previous game, but the good guy has a secondary objective. So the good guy is actually a patrol of the environment. So not only that the good guy has to always keep the bad guy under eyesight, under visibility, but it also has to maximize some short-term surveillance of the environment. So you need to keep patrolling around the environment to observe whether there's any change or any additional information that pops out in the environment, while keeping the red guy under surveillance at all time. And this is a simulation that is done, and you will see that the blue guy seems to try to follow the path indicated by the green dots, and this path indicated by the green dots are generated by solving certain kind of static games, which we'll mention later. And along the path, some check will be enforced to make sure that this the static game generated trajectory is still admissible. If it's not, then we have to revise the path according to the current state of the game, like that. Okay, and this is to show this. This page is to show that if one can, with the algorithm that we have developed, then the blue curve shows some kind of capacity of the surveillance, whereas if you just optimize the surveillance without the patrolling, then this is not, it's not optimal. So we will not talk too much about it. It's just to say that there's this other type of games. So to put our kind of discussion in a more concrete form, then it's inevitable that we put this formulas that probably people have shown, in many different talks in this conference already. So we assume that there are two players, or two groups of players, P and E. P denotes for pursuer and E denotes evader, and they are controlled. So this is the dynamics of the, and then they have, each one of them have control, sigma sub P and sigma sub E. And they start out, the good guy will start out from initial condition, initial position X, and then we will use P sub X of T comma sigma P to denote the trajectory that's generated from the initial condition X under the control sigma P, and accordingly for the evader. So these are the controls, and of course one can, so the topic of today's talk is really on how do you design feedback strategies, which we will also call policy, which is a function that takes take a state of the game, position of the pursuer and evader, and map it to an admissible control. And then if you use that to generate, and then to use this feedback to control the trajectory of the pursuer and an evader in order to achieve the objective of minimizing the cost functional or to play the game, like that. And of course, these dynamics has to be formulated in this in this domain over here, where you have obstacles, and one assume that we cannot go into the obstacles. One can go tangentially to the obstacle, but not into the obstacles or through the obstacles. Okay, so that's about feedback strategy. And a few more notations just to kind of anchor our discussions. So we're gonna use a signed distance function to represent the domain that has many obstacles. So this means that in the lower left figure, plots, you will see this obstacle, which is denoted by the point set omega sub ups. So this is the obstacle set, and the sign distance function will take the negative values inside this region, and it will be 0 at the boundary of omega sub ups. Okay, and then it will be positive outside in. So the sign distance function will be positive in the omega free region. And then we'll define the visibility function, which encodes the line of sight information. And we're going to use particularly this notion. So psi of x and y will encode the visibility or the line of sight information connecting these 2 points x and y. And it will take the minimum value of the sign distance function alone or restricted onto the line segment connecting the 2 points x and y. So therefore, therefore, psi of xy will be less than or equal to 0 if the line segment connecting x and y goes through the omega goes through the obstacle or even tangential to the obstacle. It will be the critical location where psi equals to 0. And on the lower right plot, you see the level sets of this visibility function psi, where the pink curve is the critical boundary, is the 0 level set of psi, representing the boundary between occlusion and non-occluded region, where x naught is x and y will be potentially anywhere, like that. So we're going to manipulate, and we're going to use informations by such kind of these functions to develop algorithms. Okay, so if one want to play a game where the game would end when the bad guy gets into the region enclosed by this pink region, then one can define this endgame state, which is the pair xy where psi of xy is less than 0. So this is the important set. This is the endgame state. And then we can think about 2 types of game. One type is the static games, and the other one is the feedback strategy game. So the static game is, let's say, so for this kind of game, we define this functional j, depending on the initial condition, the initial states x and y, and then the control of each one of the players. And the objective is we want, this is, so this is the smallest time, hold on. So I'm temporarily confused. Yeah, so this is the smallest time when the trajectory of P and E will get into the endgame state. And we can then try to obtain these 2 value functions. And the first one, V sub S, will give the evader an advantage in the sense that the evader gets to optimize, because the evader wants to have the game, to play the game, to end the game as soon as possible. So the evader gets to optimize with respect to any of the possible control that the pursuer comes up. And then the pursuer has to act accordingly. The pursuer has less choice in some sense. And then you have the V tilde sub S, where we give an advantage to the pursuer, which is flipping the order of the sup and inf in this case. So these are the static games where the game is played by assuming that the 2 players only know their respective initial positions, and then they close their eyes. They're going to play the game, and then they're going to choose they're going to choose the controls according to the order of the sup and inf, and then that's it. Of course, the feedback strategy game is more interesting. In this case, we can if we stick with putting the sup first, giving an evader more advantage, then we can try to define a feedback control for the pursuer, and then this will be the corresponding value function, which is denoted here by u of xy. And due to the order of we set up these sup and inf, then it's easy to understand that the value for the feedback gain will be sandwiched between these two other, the value function for the other two static gains. Okay, so I would first want to quickly review the static gains. So again, so the evader got to optimize, knowing optimize according to whatever the control the pursuer comes up. So this is an open loop type of problem. Players choose their controls at initial time and run in open loop for t greater than 0 until the endgame condition is met. The evader is given advantage, as I mentioned earlier, to make the best effort to counter any of the pursuer's control. In a previous paper, we kind of show that the static game would, for this particular static game, the game will always end in finite time if the free space is not a star domain. So the game will not carry on forever. Why consider this kind of static game? We would argue that so there are some applicable scenarios in which one can benefit from knowledge of solving static games. For example, if really only the initial state of the players is known, and then one has to do the best we can, and that would be playing this static game to optimize. Or we can try to say that we will use the controls, the optimal controls that we have computed for the static games into design more optimal feedback strategies to play the feedback, to play the optimal feedback strategies. So on the figure on the right, you will see the simulation of the algorithm that we have developed earlier, where the red is the bad guy. The bad guy will go towards this position, and then the blue guy will compute this this region that is enclosed by the blue curve. We'll select a point on the boundary of this region on this blue curve that will maximizes the end game time for this particular static games. So very quickly, this algorithm that we develop essentially kind of decouple the considerations for the evader and pursuers and allow massive parallelization to compute the necessary informations. So the algorithm will start out by assuming the initial state, the positions for the pursuer and evader, x, y, and then for each point in the free space, we're going to compute this t star sub y. This is a set. This is a value, right? And this value here will tell you that what is the time, the shortest time that the evader would need to travel into occlusion if we place the pursuer at that particular location. Okay, so this is the first function that we will compute. And then the second function is also a function of p in the free space, and it describes the pursuer's travel time from the initial location x to p with a path that has unobstructed view of the evader's path. So this is the second function that tells you gives you some advice on how the pursuer should go. The first one is, kind of try to estimate how fast the evader is going to get into occlusion. And then combining the T star and W would be this region defined by R, this region depends on the initial state, and this is all the positions in the free space at which T star minus omega minus W sub x is greater than 0. So this is a set of locations where the pursuer has the capability to reach from x before the evader will become occluded. So this is the region R. And then, so I will show you a picture later on how these three sets. And then we just pick P in this region R that maximizes T star. So that would be the algorithm for solving this particular static game. The computational complexity over here is really it is, so if you have k players, then there will be k times n to the power of d. D is the dimension. So here is what we have been seeing is 2 dimensions, and n is the let's say kind of the grid points that we put in each dimensions. And these computations are highly parallelizable. So the big O notation here is serial computations. And then we need so yeah, I will move on to the next. So this is a picture of these are two pictures of these simple static game. The blue region over here is actually denoting the region R that is defined earlier. This is T star minus W. And this is the T star. This is the graph of T star. The travel time of E into the occlusion if there's a pursuer placed at the position P. So this is like that. Of course, one can generalize that algorithm very easily to do multiple players. So here we just show a static game of 4 players, 3 bad guys and 1 good guys, and this is how optimal the game could be played. The good guy has to move from the initial states over here to this particular location, and that will allow them the longest game time. Now, if we try to say I'm gonna just move 1 step, for my current location, I'm gonna compute the static game, and I'm gonna extract the optimal control, but I'm gonna only use that optimal control to generate a very short segment, generate a trajectory for a very short segment, and after that short time, I'm gonna reevaluate the situations. Then I could essentially when I reevaluate, the optimal control coming from the new refreshed state would give then it could serve as the feedback control, and so that's one application of solving this static games. So here on the bottom part of the screen, you see the initial state on the left, and then the middle part is the static game, where the good guy has just go away from the obstacles, and where the bad guy will try to go very quickly tangential to the obstacles. But if you allow this feedback based on solution to the static games, then you see that the blue guy actually knows it has to follow the red guy in some sense while keeping a distance, like that. Okay. So that's making a static, a sequence of solving a sequence of static games to provide feedbacks to play the game for longer time. Now, one can also consider kind of relaxing the situation a little bit. So this is just to illustrate, kind of the point that we're going to make later on. So we can consider, again, this visibility function that encodes the line of sight information, and then the cost function, I'm going to relax it. So we're not going to be so strict as the moment the bad guy vanishes from the eyesight and the game ends. But instead, I'm going to define this cost function as follows, where this is the terminal cost, and the terminal cost would be very high when P and E cannot see each other, and the running cost is the same. The running cost will be very high when P and E cannot see each other. Otherwise, it will be smaller. And of course, the good guy. So then we can easily derive a finite horizon, and we play this as a finite horizon game. Then the good guy will maximize J, and then the bad guy, the evader, will maximize J, while the good guy will minimize the game. Then one can easily derive these. I forgot this. One can easily derive this Hamilton-Jacobi Isaacs equation of the following form, which is it could be in the dimensionality could be pretty high. And here I deliberately not write down the initial conditions and the boundary conditions. The boundary conditions will be related and will be related to the end game states. and the initial condition will be just the terminal cost, like that. And we try to solve this just to get a peace of mind and see how this will go. So we try to solve this very simple problem, which is the state space is 4 dimensions, and then there's a time dimension, so it's a total of 5 dimensions. And we solved this on I think something around 30 by 30 by 30 by 30 grid. That's already kind of it's not easy to go much higher due to the power of 4 kind of increments. So, and then we extract the trajectories this way. The bad guy is gonna get closer to the obstacles and then kind of circle around. And then the good guys will try to keep a distance and try to follow the bad guys like that. Okay, so this is the optimal, trajectories extracted from the solution of the Hamilton-Jacobi Isaacs equation like that. But the problem is, of course, we cannot even do it in 3D. This simple game in 3D, solving this equation easily. And of course, this is relevant to this workshop because there are many experts developing numerical methods for solving high-dimensional Hamilton-Jacobi equations. So this is one highly relevant thing. And we're going to do something different. So there's this type of surveillance evasion game, of course, has been considered. The earliest we can found is papers in the 1979, in the 70s, and then 90s. Continuously, there are people considering this kind of problems. And I've been developing algorithms involving optimizations related to line of sight, and that's why I'm here talking about this particular topic. Then there are so recently there are a couple of interesting papers that pops out. Let's say paper number 2 by Gil and Vladimirski and all, where they consider evasive path planning under surveillance of uncertainties. So they, etc. So now we come to what this is, in some sense, the second half of this talk, where I'm going to talk about search algorithms. So we would like to we would like to use some kind of deep learning strategy to learn the policy and the value for this kind of games. The first thing is that so this will probably have to be formulated as a supervised training algorithm. Problems. So then we need to generate data. We need to generate training data. And what is the training data? So we're deeply motivated by the success of Google's AlphaGo 0, in which they used Monte-Carlo-Tree Search to come up with optimal strategies in playing this game of Go. And so our idea is whether we can do something similar here. To play this kind of line of sight based games. So we're gonna develop Monte-Carlo-Tree Search algorithm to sample possible trajectories and use these samples to refine the policies, meaning the feedback controls. And then we're gonna play the games until either the game will win or lose, or until a maximum number of time budgets. And then the results, from the results, we're gonna gather those results and use them as training data to train a neural network for the policy, and then a neural network for the value function. Okay, so this will be clear later on. So the training generate training data for neural networks. And furthermore, when we play the game, we would like to use Monte-Carlo-Tree Search online, coupled with a generated neural network to play the games, to further refine the policy of and the performance of online game playing. So as I mentioned, we consider Google AlphaGo style Monte-Carlo-Tree Search algorithm. Why? So we were hoping that, so the first thing is that everybody in this workshop will probably acknowledge that it's very difficult to solve, in particular, variable coefficient Hamilton-Jacobi Isaacs equation in high dimensions by any traditional PDE methods, just impossible due to curse of dimensionalities. And furthermore, we would like to consider situations in which, for practical matters, maybe we would like to play the game in different types of environments. So you have different types of omega obstacles. But you can say that perhaps the environment all looks the same. For example, if you're playing this cat and mouse game in the city, in an urban setup, then we can say that the urban obstacles and their arrangement, they may be different, but they have some kind of similarity over there. So this might be an opportunity for the neural networks strategies to kind of parameterize and learn how optimal policies and optimal values, how they depend and vary on when the geometry of the environment change. They're similar, but they're different. So we are also thinking that this is really relevant if we're thinking about reinforcement learning, and we're thinking about developing kind of instead of a one classical greedy algorithm. We think about, we want to do multiple step look ahead. We want to optimize certain objectives after the total rewards after five steps or after 10 steps, instead of just after maximizing the total reward after one step. So multiple step greedy algorithms, and we thought that the strategy that we're trying to develop might be of use in that regard as well. Okay, so what is Monte-Carlo-Tree Search? Well, I will show you this video clip. It kind of shows you, it gives you a flavor of how the search is doing. You will see, this color being flickering around the two the states, the blue dot and the red dot. And this color actually shows you a normalized version of this function n. The more frequent this a particular node, a particular grid is visited, then the deeper green it will be. Okay, and in the end, when you try to use so in the end, this Monte-Carlo-Tree search will try to visit certain neighboring grid nodes or neighboring states from your initial states, following this rule. And this rule has two components. One is called Q, and the other one is called P plus noise times some normalization factors over here. The first blue box is, in some sense, it's related to exploitation. You have seen something that looks that kind of performs well statistically. You're gonna further refine in that. You have sampled some path that seems to last longer. Then you're gonna sample the nearby path more. This is the exploitation part. And then the exploration part, you see the presence of noise tells you that perhaps you need to take a big jump ahead to some other state in order to discover those paths that you have previously have not sampled and could be potentially more optimal. So, and then you sample this function and you call it U, and which is a function of your current state and the possible actions or possible policy related to the state, and then you try to maximize that. And so the next node, next state in the search will be determined by this A star and from the current state. So A star will take you from current state to the next state like that. So N is the number of times during the search where the player is employed the control A at a state S. Okay, so N is updated, as your Monte Carlo search is going on, and then Q is kind of like a win ratio something like what's the possibility of winning, or what's the statistics of winning if you have a path that goes out from S, taking the policy A like that, and P is the policy that would eventually will be replaced by a neural network policy. Okay, so next step. So then after we have done this, so this is to generate many steps in the search that you go on and you explore the neighborhoods of the initial states. Then you along these along this sampling, then you will compute this n, this function n, and then you will compute the function q, and then with that, when you finish one search, for example, here I used this notation. So this is Monte-Carlo-Tree Search, 500 steps of Monte-Carlo-Tree Search using a predefined policy P. Then you look at the statistics, and then you take and then your feedback is defined by maximizing this particular number n, and then you use that policy that feedback into here to find the next step when you try to play the game. Okay, so this way, Monte-Carlo-Tree Search, we can use this. We call it self-play, right? Following Google's language, you self-play. You let Monte-Carlo-Tree. You randomly select a whole set of initial states, and then from each one of these initial states, you just play the game with Monte-Carlo-Tree Search, and then you would generate this kind of triple as data. Where S and N will be used to train the policy network piece of theta, and then this V. So this V is actually the true value in some sense, the value of the game. If you this part of the data S and V will generate and will be used to provide to be trained. Will be used to train a value network, V sub theta. And this value network is going to be used inside this exploitation function Q, like that in the gameplay. So what I didn't write out here is the explicit dependence of these functions on the geometry of the environment. So if we want this kind of game to be played and the neural network to generalize to earlier to other environments, then we have to have a training set containing all relevant geometries of the obstacle sets as an outer loop, if you want to call it that way. And this way, the two neural networks will also include the dependence of the policy and the value on the geometry of the problem. So we have done that, but in a somewhat similar, simple setup, two-dimensional, two-player setup. So here, what we're seeing here is an environment containing three obstacles. Okay, these three obstacles are not, they are not in the training set. Okay, they're not in the training set. So in the training set, we have placed other similar obstacles, a different number of them, in order to train the policy network and the value network. And then on the left, what you see is this Monte-Carlo-Tree Search, where the policy P is just some random, it's random, and then you add a Dirichlet noise to this thing. This is the most classical one, and the search involves 1,000 steps. So at some point, the game, of course, the game is not played optimally. So at some point, the game ends because the red guy gets into the gray region. Now, with the trained network as a policy, so in the Monte-Carlo-Tree Search, there's this Q plus C times P times this factor over there. So the P will be replaced by the neural network pre-trained policy, and then the Q will also use the value neural network, and we use 1,000 steps. Then one can see that the game is playing for the game lasts a lot longer, but eventually the game will end. the game ends, but it lasts significantly longer than the first one without the the aid of the neural network. So now, if you during the playtime, if you do 2,000 Monte-Carlo-Tree Search step, then with the same neural network, with the same neural networks, then the game essentially lasts forever until we are tired of it and it's still playing. One can always keep the red guy in eyesight, like that. Okay, so in this process, we discovered that, well, actually, we would like to, since we're not Google, we hope that one can improve somehow the sampling capacity of Monte-Carlo tree search algorithm. So we want to improve the efficiency. We want the Monte-Carlo tree search to sample more of the relevant optimal or near optimal path more quickly. So how do you do that? We're thinking, maybe one can try to use some kind of heuristics. So the policy part of the Monte-Carlo tree search algorithm, initially is kind of some kind of random noise, but now we want to replace that initial policy by something that's kind of heuristic that we know in certain situations it performs better, and use that as an initial policy in the Monte-Carlo tree search algorithm, and see whether, given the same type of number of search steps, whether the resulting algorithm would yield more optimal solutions to the problems. Okay, so this the earlier the third bullet points was saying that, well, people have been trying to reproduce Google AlphaGo 0, but it seems that one really needs a lot of computational power to do that. Okay, so one heuristic is to say, okay, what maybe we should always, so from the perspective of the good guy, in order for me to get good, I need to play with a qualified opponent. I need to play with a very good opponent. So this means that one needs to train with a good evader as well. So well, if we think that, if we can use the following logic to come up with a strategy to get a more optimal evader. Namely, if you assume that the pursuer is stationary, then in the Hamilton-Jacobi equations, the gradient with respect to the pursuer is gone. Then what's left is just an iconal equation of the pursuer of the evader in the free space. So therefore, if the pursuer is stationary, one can say that the best strategy for the evader is to just try to get to the endgame state as soon as possible, solving this, and this can be accomplished by solving this particular iconal equation and extract the optimal path based on the right conditions here, boundary conditions here. Then, of course, we would like to. So we're thinking in the context where it's a discrete time kind of games where pursuer remains is assumed to be stationary, and then we play the evader like that. So this is the logic of the locally, we call it locally optimal evader. What about the pursuers? So we are going to discuss two strategies for the pursuers. So the first pursuer is rather simple. We just say that we're going to try to stay close to the evader as much as possible, because if I travel identical to the evader, then I can always stay with the evader, and they will never lose my eyesight. So this is the first type of strategy, and you will see that later. This will lead to something like a cat and mouse game where you just keep trying to keep and follow the evader, and eventually evader get a chance due to the geometry and then just vanish from your eyesight. And this is shown over here in the simulations. So the color map that you see over here, from yellow to green, tells you some kind of distance, shows you the distance. So in a sense, it shows you the policy of how for the pursuer to use to play this game. So let me So we play this game. And then eventually the evader get a chance and then just vanish. And this chance is due to geometry of the problem. So this is a frozen thing. So after playing around the corner for a while, the evader get a chance to just hide in the shadow, and then the game will end. So so the policy leads to cat and mouse chase, where P moves to E's previous location, and near obstacles, the occlusions are larger. So E wins by jumping behind the obstacles when the opportunity pops out. So the second type of strategy is motivated by the static game, and we call it steer the shadow away strategy. So in some sense, we're gonna move the pursuer to a location where the shadow, the end game set, so where the shadow line is the farthest away from the evader as possible. So then this is computationally more extensive, and in general, there's a tendency for the pursuer to move farther away from the obstacles because the shadow gets smaller. But it so happened that when you move far away from the obstacles, you might be also too far away from the evader, and the evader again get a window, a sliver of windows of chance to vanish from your eyesight. And this is the simulations of that. It doesn't try to close into the evader. It tries to stay a little bit away, but when you're too much away and due to the geometry, the evader just hop in over here, and then you're over. The game is over, like that. So so this avoids the cat and mouse game, but it creates some other problems. So in either situation, what one can say is that the pursuer does not really fully utilize the dynamics of this the gray line, the shadow boundary, or the frontier in some community. This set is called the frontier. Does not fully utilizes the dynamics of these frontiers to come up with optimal feedback. So then you can always find situations where one of the two strategies will be inferior. So this is a gameplay for 5 players using this kind of policy. So what you're seeing, what's playing on the left is the get closer policy. Eventually, the pursuer would lose, like that. And this is pursuer will use the sear the shadow kind of policy. And in this simple setup, the pursuer will find eventually a good set of locations where they have very good visual command of the environment, and the game would just last because there's no way the red guy the evader would hide. Okay. Now, this will show you, in this slides, we're going to show you how the get closer policy can be improved by Monte-Carlo-Tree Search. Okay, so on the left side, we essentially don't use Monte-Carlo-Tree Search. It was a 0-step of Monte-Carlo-Tree Search, and this is a 4-player game. It just very quickly the red guy get into the shadow, and then the game is over. So for the same initial condition, excuse
me, Richard, that I'm interrupting you. So you just have about 1 minute left.
Yeah, I'm close to be done. Okay, maybe 2 minutes.
Sure.
So if you employ 500 Monte-Carlo-Tree search using the same initial policy, the game lasts much longer, like that. Okay. So the dividing difference is, so you see that the trajectory start to deviate if you look at over here and over here. So after Monte-Carlo-Tree Search, there's absolute sampling nearby trajectories, and the policy is refined to be steering the blue square over to this point instead of trying to get closer to this red guy. And that made a difference. That minor difference in this instance accumulatively allow the games to be played much longer. Okay, so this is the effect of incorporating some Monte-Carlo-Tree Search. And we're also interested, we're interested in, kind of statistics of Monte-Carlo-Tree Search with respect to different policy and different number of steps. So very quickly, the horizontal axes, so we'll record how many, the time of the game that plays. We're gonna compare some kind of statistics using involving Monte-Carlo-Tree Search, using 100, ranging from 100 steps to 1,000 steps. And then in each color in the following figure, you will see, so the blue one is some statistics, it's the statistics of the games when one use 100 Monte-Carlo-Tree Search step. And the orange one would be 200, etc., increase all the way up to 1,000. The horizontal axis denotes the game time, okay, and the vertical axis is somehow the density, the normalized, the quantity normalized from the total number of games that's played. Okay, so in this figure over here, upper left corner, that's the straightforward Monte-Carlo search with Dirichlet noise. This is the distribution that you see. Of course, we would like the distribution to shift more to the right, the better, because that means that the game would, on average, play much longer. The upper right is the neural network, 1,000 steps, total 1,000 step neural network. Then you see that starting from 100 steps all the way to here, the distribution started to shift to the right. And this is with the steer shadow policy. And then the lower right is the uniform noise. This is the performance of worst. And you also see the statistics, the average game time and the standard deviation. So this is, so what one reads from here is to say that, well, there is some merit to use Monte-Carlo search, and then there's also some merit to use a deep neural network, deep neural network to kind of encode, to learn the optimality of these controls that will allow you to have more efficient search. And finally, we're further going to compare. So how about I compare, Monte-Carlo-Tree Search with the two policies, get closer and steer shadow. And it turns out that, get closer with the 500 Monte-Carlo step seems to be much more efficient in learning how to play the game. It plays the game much more optimally than the steer shadow in the setup. That is something that's rather surprising. Because in some sense, we think that steer shadow strategy has more math in it. But at the moment, this is where this is our latest result. We're speculating that maybe we need to beef this the number of Monte-Carlo-Tree Search step to be higher in order for this steer shadow policy to be refined more efficiently, But the computational cost for this steer shadow is much higher than the get closer one. So we're not sure whether it's worth doing that or not. This is so I will skip that due to time. So this is my final slides. So there's some observation and some early thoughts in this project. So what we have demonstrated is that one can use Monte-Carlo-Tree Search to refine non-optimal policies to make them more optimal. And one needs sufficient number of steps in order to benefit, okay? So because you need sufficient number of steps, so Monte-Carlo Tree Search could be expensive if you are careless. And if we want to refine the policy, the cost for evaluating the policy during a Monte-Carlo-Tree search will become a concern, because that could, kind of be very expensive cumulatively. So to counter that, we're developing a multi-resolution version of Monte-Carlo-Tree search in order to improve the kind of the branching out of aspect of Monte-Carlo-Tree search. And one would say that this such type of algorithm is developed with the objective that we would always want to try to get a good outcome for any instance of the game, instead of saying that on average we want to have a good performance, something like that. So with that, I will end my talk, and thanks for the attention, and please stay safe.
Okay, so thank you very much, Richard, for the presentation. So I'll be taking questions now. So if someone has some questions, please raise your hand electronically or on a video. I can see now all the screens. Okay, so it seems we don't have any questions. So thanks again. Oh, wait, I think Mauricio has a question. Okay. Yes.
How do I speak?
Hi.
Okay, hi.
So, I have a question regarding the multiplayer game.
Okay.
So when you have several players and you are thinking to a model where you have a pursuit evasion game, so how do you manage several players? Because you have to define the value function. So you can define this in several ways. Either it's a pursuit evasion game where you win if you catch one evader, or you have to catch all the evaders. I mean, there are several ways you can think of regarding several players' pursuit evasion games.
Right.
So, which one are you using?
So in this, in my presentation, what we're using is just as long as one bad guy get to the end game state, then the game is over.
So when one bad guy is, so it is sufficient to catch one guy.
No, we aim at catching all the guys. We're not catching them. We just want to we want to keep them. Literally, we want to just.
No, I mean, I'm using catching because it is the typical pursuit evasion kind of terminology. In your case, you want to see them.
Yes,
okay?
And so we want to catch all of them. So in all the simulations I show you, we want to catch all of them.
Okay, so if even one of those is not inside, you lose.
Yes.
Okay.
Of course, during the search, we can revise this thing according to different objectives in catching. We can keep on searching and keep the game from keep on playing. That's also possible. So that is some flexibility that is kind of built into this kind of search setup.
Okay, but I think that in this definition that there is somewhat a problem, because I can imagine, depending on the number of obstacles you have, that in several cases it would be impossible to follow and to keep inside all the players. Yes,
definitely. So so far we're not really developing any theory on when the game would end and etc. So far, our focus has been how to come up with the algorithm that can play the game as long as possible.
Okay. So thank you.
Okay, thanks. So, are there any other questions? Okay, so it seems there are no more questions. So thanks again, Richard, for the presentation.